Okay, so today we're going to talk about metric spaces, which are a really great way to see some concrete applications of topology. Indeed, a lot of courses on point set topology start with the idea of metric spaces because um, the ordinary Euclidean space is an example, and there are many other familiar examples of metric spaces. So, um, a metric space normally written as something like xd, is a set x, a non-empty set, and a function d, which maps pairs of elements in x to real numbers. So we could say that it's a mapping from the Cartesian product of x with itself to the set of real numbers. But basically, we just associate each pair of elements from x with a number. That's all D does. So it does this in a way such that for every pair of elements, we have the following conditions holding. Firstly, we have that, so for every pair of elements A and B and X, we have that D, A, B is non-negative, and also that it's only 0 when A equals B. Okay, so we also have that DAB equals 0 if and only if A equals B. So actually this is kind of like two conditions in one. Now, it's really a good idea as you're thinking about these definitions to think of D as a distance. It's kind of like the distance between A and B. So in our everyday intuition of distances, they are always non-negative, and the only time the distance between a pair of things is 0 is when those things are in identical places, or identical, if you like. Second condition is that DAB equals DBA. We want symmetry. And the third condition, the most sophisticated one, is that, oh, excuse me. Oh, yeah, okay, so I'll rewrite it. So if we have three elements from this set X, then we have that they always satisfy this thing called the triangle inequality, which basically means that the distance from A to C, or DAC, is always less than or equal to DAB plus DBC. So I think it's this third condition which really captures the essence of this thing being a something like a space, something like a space with distances and things. So when these three conditions are satisfied, then we say that D is a metric on X. So if we just think about this screen as a ordinary two-dimensional space with the ordinary two-dimensional metric or distance measure, then it's easy to see that the triangle inequality holds. If we have 3 points, A, B, and C, then of course the distance from A to C is going to be less than or equal to the distance from A to B plus the distance from B to C. And often we just refer to this kind of idea as, we just refer to this quantity here as the distance from A to B. So usually a good argument for this is that, well, I mean, obviously a bit more mathematically, but you'd say something like, well, you can get from A to C by first going from A to B and then going from B to C. And so this distance must be less than or equal to this. Okay then, so probably the simplest example of a metric space is where we have the set of real numbers and our metric or distance measure d is the absolute value function. So when we have that DAB is equal to the absolute value of the difference between A and B. So for example, the absolute value between 7 and 3 would be 4. So the first thing I'd like you to do to try and understand the idea of metric spaces is to try and show that this is actually a metric and that this satisfies the 3 conditions which I just talked about. So in particular, what we want to do is we want to show that for every A, B, and C belonging to the reals, we have that our first condition is satisfied. I'll switch to black. That we have that the absolute difference between A and B is non-negative, and that it's only equal to 0 when A is actually equal to B. Secondly, we need to show the symmetry. So these first 2 conditions are almost immediately obvious. The third condition takes a little bit more proving. That the absolute difference between A and C is going to be less than or equal to the absolute difference between A and B, plus the absolute distance between B and C. And this is a fairly important example because this is the thing holding in 1 dimension, but one can scale up this idea into higher dimensional spaces. Anyway, this case is also important for reasons which you might guess when I say it's called the Euclidean metric. You see, what we're going to do in this lecture is relate all these ideas of metrics to all the older ideas of open sets and closed sets and topology. And so you can see how metrics give rise to topologies. And in fact, the Euclidean metric gives rise to the Euclidean topology on the real line. So this is a very important example. And that's why I suggest you go through it and make sure you understand why this is a metric space. Okay, so the other example I just showed you with a little picture of a triangle, and that is basically that the idea that the ordinary style distance on a plane is a metric space. It gives rise to a metric space. So when we have our set to be the set of all pairs of real numbers, in other words, the real plane, and this time our metric D is going to be defined such that let me write the plane like this. Okay, so it's obviously a mapping from the plane to the reals, and it's such that for any pair of points A1, A2, B1, B2, we have that it's equal to the square root of A1 minus B1 all squared plus A2 minus B2 all squared. This is probably quite familiar to you. Maybe a nicer way to think of it is that this quantity here squared, this quantity here squared is equal to this quantity here squared plus this quantity here squared. But anyway, that's just Pythagoras' theorem. But this is the definition of a metric as written here with the square root sign included. So you can draw it out. You'd have a point here, A1, A2, and another point here, B1, B2. It's actually not such a smart idea to draw them in a. Let's draw it up here. Okay, so basically what we're saying here is that the distance between this point and this point, which is written like this, is equal to this length squared plus this length squared, all square rooted, which will indeed give you this length here according to Pythagoras' theorem. So this is just your normal idea of a distance measure in 2D space. Okay, another more interesting example of a metric space. So there are lots and lots of very useful and interesting examples. And so far I've shown you things which are probably quite familiar. This is something which is a bit new for people who haven't looked at a lot of topology before. Very important. If you have any set at all that's non-empty, then you can define a metric on it. Which is such that for every pair of numbers in that set, for every pair of elements in that set, we just have that the distance between them is, so this distance is equal to 0 if they're equal to each other, and it's equal to 1 if they're not equal to each other. And again, I think it's fairly important that you prove that this is a metric space. It's not really too difficult, and this is called the discrete metric. So you might be thinking maybe it has something to do with the discrete space, and you'd be correct. And just before we get into how metric spaces relate to the other topological ideas, let me show you one more, much more sort of exotic and interesting idea of a metric space. So this is going to involve a little bit of calculus. So if you haven't done much calculus before, then you know, you can just ignore this safely. It's not going to be a central part of the course. It's just a definition. I mean, it's just an example. So let's let C 0, 1 be the set of all mappings F which are mappings from the unit interval to the unit interval. Okay, so this is quite a quite a big thing to try and wrap your head around. So, for example, I'll do it pictorially. 0, 1, 0, 1. Here's a mapping from the set to itself. So that's a member of this set here. Here is another one, and there are lots and lots and lots of them, of course. So we're talking about the set of all mappings from a unit interval to itself, and that's our set. And we want to define a metric on that set. Is going to be equal to the integral from 0 to 1 of the absolute difference between f of x and g of x as x varies from 0 to 1. So pictorially, we've got our unit interval here, and let's say this function here is this is f, and let's say this function here is g, and so our measure of distance between these pair of functions is the difference in area between these two, the difference in the area underneath these two functions, which you could think of as just shading in the kind of distance enclosed between these two functions and sort of totaling that distance as an integration. And that's the measure of distance between these two functions. And again, it's a very interesting exercise to check that this thing here is indeed a metric. Okay, so now we're going to define the idea of an open ball around a general point in a general metric space. So let's xd be a metric space, d being a metric on the space x, and now let's suppose that we've got some real number r, and let's suppose we've got some points inside our space, and now we're going to define something. So we're going to define the open ball about a of radius r, and maybe you can actually guess what what form this has. We're going to write it as capital B subscript R of A, and it's just equal to the set of all points which are within a distance R of A in our metric space. So it's equal to the set of all elements x, little x, which are a member of our space, which have a distance from R, which is actually less than, which have a distance from A, which is less than R. Okay? It's a set of all points in big X such that the distance of those points from A is less than R. So if we're talking about the Euclidean plane with the metric I was just discussing involving the square root, then if this is a point A1, A2, then the ball around this point of some radius would look something like this, although it would probably be a bit more round. Okay then, so it's interesting to think about different metrics in the plane and what the different so-called open balls look like. I mean, obviously, this concept of an open ball works well if you're thinking about Euclidean three-dimensional space, because it is literally then a ball. But when you think about many other metrics, it doesn't look so much like a ball. So let's define some more metrics on the plane and think about what these balls look like. So this is one of my favorite metrics. It's called the taxicab or Manhattan metric. And so suppose we've got a pair of points, A1, A2, B1, B2 in the plane. And now I'll call it the Manhattan distance, but it's basically just a metric. The Manhattan distance between these pair of points is defined to be equal to the absolute difference between A1 and A2 and B1, excuse me, plus the absolute difference between A2 and B2. Okay, so the reason why this is called the taxicab metric or the Manhattan metric is because if you think about, sorry, I'll use a different color. If you think about a city like New York, which has a lot of blocks, and you're a taxi driver, then if you want to get from one point to another, then of course you can't go in a straight line because you can't just travel straight through buildings. So the actual driving distance for you is going to be equal to the sort of total horizontal displacement plus the total vertical displacement. And you could go many different ways, but still end up having to travel at least the Manhattan distance, which is given by this metric here. But what we're interested in now is what does a ball look like in this metric? So perhaps you'd like to pause the video and see if you can sketch what kind of shape a ball would have under this kind of metric. Okay, so it basically looks something like this. I'll draw it in blue. So let's say this point in the middle here was 0, 0, and this distance here was 1. So all the set of points enclosed within this sort of blue diamond here, this would be equal to B1 of 0, 0. Because each of these lines is defined so that you know, the horizontal distance plus the vertical distance away from the 0, 0 point is equal to 1. Okay then. So now let's start to talk. Okay, just before I start to go on to the connections with topology, which are of sort of most central interest to us, I also just want to mention that the norm of a vector space on the reals of the complex numbers is also a very important source of metrics, and there's lots of connections there with things from linear algebra, but I'm not going to talk about them, which is why I just put it as a side note for someone to Wikipedia who's interested. Okay then, so what we're going to do now is we're going to connect the idea of metric spaces with the idea of topology. This is a massively important connection because basically loads and loads of the mathematical objects you'll be familiar with are metric spaces, and once we have this connection, we can apply all the ideas from all the previous lectures to metric spaces. So this is the crucial lemma. And what it says is that, well, let's write it out properly. Let XD be a metric space. And suppose we've got a pair of points in that space, A and B. And also let's suppose that we have a couple of positive numbers, delta 1 and delta 2. Now here's the points. If we have a point C, which is within the open ball of radius delta 1 about point A, and it's also within the open ball of radius delta 2 about the point B, then there's going to exist another number, which you'll just call delta, which is such that there is an open ball of radius delta about this point C, which is completely contained within the intersection of the radius delta 1 open ball about A and the radius delta 2 open ball about B. Now I'm going to leave the proof to this for you. The key notion of it, I think, is to think about what this lemma means in 2 dimensions and draw a diagram. So I'm going to show you that diagram in a second, but I recommend you pause the video now and try and think about how do you sketch this lemma in 2 dimensions, because once you've done that, sort of becomes obvious what you have to do. Well, okay then, so here's how you can work it out. Let's suppose you've got a point, we'll use a different colour. Suppose you've got a point A here and a radius delta 1. More of an ellipse, but what can you do? Here's another point B of radius delta 2. And so now what we're saying is if we have a point inside here, C, then we can find a distance, delta, little delta, draw it in there, such that there's a ball around here which is contained within this kind of intersection area between these two different balls. So let's just zoom in this a bit, so it kind of look like we have this point C and this distance delta, and we should be able to construct a ball around C of radius delta, which is contained within the intersection of those two balls. So basically that's the kind of pictorial idea, but you should try and prove that this holds for every metric space. So an important corollary of that lemma is that if we have a metric space XD, with a couple of open balls, B1 and B2, then, then we're going to have that the intersection of those balls is going to be the union of open balls, of some open balls. From this metric space. So we have that the intersection of a pair of open balls is given by the union of a load of open balls. So now finally we can make our link with topology. So if we let XD be a metric space, then it follows from our last corollary that the collection of open balls in our metric space is a basis for a topology tau on X. Okay, so if you get all of the open balls from a metric space, then that forms a basis for some topology on the set that that metric is defined upon. And we call tau, we call this thing here, we call it the topology induced by the metric space D. Okay, so this is like a central bridge result. So I just want to be very clear about what all these different concepts mean. So firstly, the idea of a basis. I talked about this idea a lot in lecture 3, but I might as well remind you. Essentially, B is going to be a basis for a topological space when every open set is going to be equal to the union of some members of B. That's the definition of a basis. But then, why is this proposition true? And why is this? Well, basically, it harkens back to something I was discussing in lecture 3. So let's discuss this again. Might as well just recap. So I might as well just quickly remind you of the whole proposition. Essentially, what it says is that if we have a non-empty set X, and we have some collection, some collection B of subsets of X, then we're going to have that be as a basis of a topology on X if and only if we have two conditions holding. Firstly, we want to have that the entire set is equal to the union of elements from B. And secondly, we want to have that if we take any pair of elements from B, then we want to have that the intersection of those elements is the union of some elements from B. So this is something I hope we discussed in lecture 3. Anyway, it's a important proposition, and it's basically what allows us to link from the concept of metric spaces to the concept of topology, because if we think of B here as the set of all open balls in a metric space, then of course it's true that if we take the union of all of the open balls, then we're going to get the entire space, the entire set. And also we've just been arguing that if we take a pair of open balls and we look at the intersection between them, then we can, if we look at any point in there, we can find a ball around it. So, of course, we can create this intersection as the union of different open balls if we have a metric space. So we have this and we have this for our set of open balls of a metric space. Therefore, we get a basis of a topology. So then we connect with all the other ideas that we're talking about. Of course, we haven't discussed what topology. We haven't discussed exactly how, what is actually the form of this topology. But we'll be thinking about that some more. Okay then, so let's have a look at an explicit example of the previous proposition. about metric spaces actually working. So let's consider the Euclidean metric on the real number line. So I suppose D is this Euclidean metric on the real number line. And now what we have is that the set of all open balls around points on the number line with respect to its metric. Okay, so let's just recall an open ball of radius delta around a point A in the reals it's going to be equal to the set of all x in the reals such that the absolute distance between x and A has got to be less than delta. So when we have this, then it's pretty clear, hopefully, that the set of all open balls around the set of all points with different radii is actually going to be a basis for the Euclidean topology on R. So we're going to have that that's going to be a basis for the Euclidean topology of R. And to see this a little bit more clearly, just think about what this actually is. Essentially, it's just equal to the open interval, A minus delta, all the way up to A plus delta. So the collection of all things like that is a basis for the real numbers. We discussed this again in lecture 3. Okay, so I've just written a couple of metrics here. This first one is called the Euclidean metric. On the plane, studied since antiquity. And this one is the Manhattan metric, or taxicab metric. Okay, so this second metric here, this is called the taxicab metric, as I've already discussed. And also remember the shapes of the different balls that these things define. I mean, the ball defined by the Euclidean metric is just like a circle. The ball defined by the taxicab metric looks more like a diamond. Okay. Now, what's interesting is to think about what kind of topology these metrics induce via the thing of the previous proposition. So, you know, the set of all open balls from a given metric space defines a basis, which defines topology. So, and that means that the metric space induces a topology. So, what kind of topologies on the plane do these two metric spaces induce? Well, surprisingly, they actually both induce the same topology, the Euclidean topology on the plane. So, sometimes different metrics can induce the same topology. So, to formalize this idea, we say metrics are equivalent. on some set X, and when they induce the same topology. It's a very good exercise to solidify your understanding of the connection between metric spaces and topology, to show that both of these induce the same topology on X, on the plane. Okay then, so I think the final proposition of the day will let xd. Okay, so here's another proposition. We'll let xd be a metric space, and let tau be the topology induced on X by this metric D. And then what we'll have, then we propose that if we have a subset of X, then that's going to be open if and only if we have that for every member of that subset, there's going to exist some positive number epsilon, such that there's going to be some epsilon radiused ball around that point A, which is contained within U. Okay, so this gives us a much more explicit connection between what the topology is and the actual open sets. And so you can prove this as an exercise.